Hi everyone, and welcome to this lecture of ModSim 2 on applications and practical considerations for population balance models. In the previous lectures by my colleagues, you have had a sound introduction into population balance models. So by now you should have some basic knowledge on what a PBM is, what it consists of, and how it is represented. You also know what different physical mechanisms can be modeled using a PBM, such as aggregation, breakage, and growth, and how these look like in the model. Further, you have had an introduction into the rate processes, and finally the solution methods on how to actually solve this monster of an integral partial differential equation. On this knowledge, we will build up some interesting applications in this presentation. So these applications will fall into three main categories. The first one is how to calibrate the population balance model. The second one is what you should take into consideration when designing a new kernel for a specific PBM problem. And finally, something that is often overlooked, how can you get some confidence bands on your model predictions? Because you do not only want to calibrate your model, you also want to have an idea of the quality of the prediction related to the quality of your experimental data. So if you want to calibrate a model, you first need to select the mechanisms that are occurring in the system. And this will, of course, depend highly on the system under study. So in this presentation, I will show some examples from a continuous pharmaceutical production line, which transforms powder into tablets. You do not need to know all the details of this production line, just that it transforms a blend of dry powder into wet granules, which are then dried, milled, and pressed into tablets. More specifically, we will be looking at this unit operation, the twin screw wet granulator. It transforms a dry powder into larger wet granules. The co-rotating screws make sure that everything is well mixed on the cross-section of the system. In this application, the wet powder particles can stick together or break apart due to shear stress. So this is focusing on the mechanisms of aggregation and breakage. So as an example, the initial dry pre-blend could look like the gray line in the graph in the middle, which is then transformed as the material moves through the system, indicated by the colored lines on the same plot. For aggregation, you could use this equation to describe the system. The idea is that because of the wetting, there are some dry particles that do not aggregate fast. But if a critical size limit is reached, particles will aggregate significantly faster. So if you need a visual aid, the figure on the right describes the Hall collision frequency. The figure on the left is a plot of the first product term. So I advise you now to pause this video. Make sure that all of this makes sense, because we will need it a couple of times later in this presentation. For breakage, this equation is used for the daughter distribution. It consists of a part of the monoparticle breaking into small fines, and the remainder of the particle breaks uniformly. So if you understand this equation, you should be able to understand and explain why it is possible that we can use this equation to transform the red line in the figure on the left into the green line just by aggregation and using this breakage kernel. So now that we have our kernel definitions, we need to look at all the parameters. How many parameters do we need to estimate from data? Can some of these parameters be kept constant, or can we derive them directly from data? So now, if you have understood previous slides correctly, you understand that the first bump of the green particle size distribution are in fact small particles that are formed by attrition. So if this peak is the same for different experiments, we can estimate the mean and the standard deviation directly from the data. This is nice because in that way there are two parameters less that you need to calibrate. Now we need to define the objective function for this whole endeavor. And the objective function is the thing that you want to optimize, or in other words, the distance between the measured particle size distribution and the simulated particle size distribution. I'm not going to detail in this presentation on how you can investigate this and what different type of distances there exist. So if you're interested, you can check the references at the end of this presentation. Further, it's nice that you have a distance function with a clear interpretation and you know how it behaves and that it's sensitive to the features and the small changes that you want to capture. For instance, a measure with a clear physical meaning is the Earth mover's distance. This distance is the optimal cost if you want to transport a heap of dirt to a hole of a specific shape, which is shown here in a figure on the bottom right. So at this point we have our model that has its specific structure and kernels, and we have determined what parameters we need to estimate and what the distance is between the simulated and the measured distribution. Now what the rest says is to have an algorithm that can explore the parameter space and minimize the distance between the simulation and experiment by altering the parameters. As an example of what you have likely seen in other courses is gradient descent. So in gradient descent you are moving in your parameter space along the direction of the steepest gradient. So in other words, the direction where the objective function decreases the most. However, some notes here, PBMs are very slow, so in the order of seconds for a single computation. To speed this up, it would be nice that we can test multiple parameter combinations at once. So particle swarm optimization is a nice algorithm where different actors can explore the parameter space simultaneously, so we can leverage parallel computation to get to a solution faster. So if you want to have a more broader introduction to optimization theory and some of these different theories and algorithms, I can highly recommend the course by Michiel Stok. It's selected topics in the mathematical optimization. So this concludes the first part of the talk. We will now continue with more details on considerations you should take when you want to design your own custom kernels. So what you have to think about when designing a new kernel. So first of all, let's compare to, for instance, a time series models as you have seen in MATSIM. So for instance, the Michaelis-Menten equation. So if you want to have more precision in that equation, well then you need to simply increase the sample frequency. The analog for a PBM would be to increase the sample frequency for the external coordinate. So in our example, this is already an issue because we simply cannot cut our machine in half to obtain more data. However, increasing the sample frequency does not solve the issue with internal coordinates. So remember that the internal coordinates of this PBM problem is particle size. So most of the time you are here bound by measurement issues. So if you decrease the size of the bins, you will get a huge increase in measurement noise, which would render all your efforts to increase the power of the model rather useless. Further, it should be noted that computational time more or less increases with the size of the grid squared. So we see that in practice there will almost always be discretization issues baked into the population balance model itself. So this discretization leads to issues, and this is mainly in the case of large sudden changes in kernel values. So do you still remember the contour plots from a couple of slides back? Well, this is a nice example of large sudden changes in a certain region. So at this point I suggest that you pause this video, go a few slides back and make sure that you recall how this aggregation kernel is working. So if we would alter the location of the large increase in kernel values while keeping all the other things the same, we would get a figure such as the one in the upper left corner, where we plot the distance between the simulation and the measurement in function of a single parameter. And you can see that there are some strange plateaus visible, and the objective function does not have a nice smooth behavior. So let us now zoom in on a specific region of this aggregation kernel, denoted with the red line in the upper right. If we would make the same plot in just one dimension, we get the plots in the bottom row. So for different values of r, such as in the top left plot, we would get different locations of the sudden increase, or as we would call it, the step, as you can see in the bottom left figure. But this is not how it is seen in the model itself. For that we need to look at how it is discretized, so how it's plotted on the bottom right. The steps that were nicely separated in the bottom left figure are now not distinguishable due to the discretization of the grid. So in other words, you have several values of for a parameter for which the result is the same. This explains the occurrence of the different plateaus in the top left figures. So for this problem, there are multiple ways in which you can solve this problem. So I suggest you try to find one, and a good start would be to look at the definition of the aggregation kernel a couple of slides back. So in the second part of this presentation, I have shown you an example of how unintuitive issues can arise from limitations in the model structure. So now we arrive at the last part of the talk. It is about assessing the quality of the model prediction based on the measurement data. So for computing some confidence intervals, we will combine different ideas. So we will start from the objective function values. So if you have performed a good design of experiments, you also have some data on repeated experiments. So from these experiments, you can compute the pairwise distance between different measurements. This will give you an idea of the natural variability in the process. So note that this variability is a combination of error in handling of the material, measurement uncertainty, and just plain natural variability of the process. This distance can be interpreted as the maximal practical accuracy that you can achieve when calibrating a model. So for instance, if you look at the figure on the top right, the average distance between repeated measurements is denoted with a yellow line. So in the whole range of R2 values, for which the objective function value is lower than that average, it indicates the range of parameters for which the simulated particle size distribution is within measurement error of the measured one. So if you now have this distance, you can look at all the parameter combinations that fall within these bounds. The plot on the left indicates this whole range of experiments for which the simulated particle size distribution falls within measurement error of the measured particle size distribution. So if we can find all these different parameter combinations with a measurement error, we can simulate all these particle size distributions. So if we combine all the different particle size distributions, we can plot some error bands around our calibrated particle size distribution. So this error band is the minimum and maximum value of all the simulations that we have performed for all the parameter combinations that you see on the left. We can also now combine this information for multiple locations in your machine. So know that you have an idea. So now you have an idea of a simulated particle size distribution on different locations inside the barrel, as well as an idea on its measurement quality. So a final thing to think about here would be, how will all these simulations change if you change the kernel, or if you have a change in measurement quality? A final thing for which we can use the uncertainty of the simulation is by mapping different experimental settings. So in the figure on the bottom left, each gray blob is are the parameter combinations within measurement error for one experimental setting in our design of experiments. So I advise you now to think about, what does it mean when there are different zones that are overlapping, and how can we create zones that do not overlap? So this is all I have for you in this lecture. If you want to have some more background information, you can check the works that are listed here.